cut 2 narrow slits in a card, hold it up to a lamp, and the wall behind it fills with something that should not be there. Not 2 lines of light, but a row of bright bands split by stripes of perfect dark. That pattern is the signature of a wave, and for 2 centuries it was simply how we knew what light was. But here is what they leave out. Send that light through the 2 slits one single particle at a time, so gently that only one is ever in flight, and the bands still slowly build, as though each lonely particle passed through both openings at once and interfered with itself. And the instant you place a detector to catch which slit it truly used, the pattern vanishes. The looking changes the result, which leaves one quiet, staggering question. Is the world definite when no one is watching, or does reality wait until it is seen? Before we begin, if questions like this are how you like to fall asleep, a quiet like or subscribe genuinely helps this small channel grow, and it means more to me than you know. Now, let's begin. Part 1. The simplest experiment that should not be strange. There is an experiment so simple that you could sketch it on the back of a receipt, and yet the people who understand it best have spent 100 years arguing about what it means. It has no moving parts to speak of. It needs a source of something, a wall with 2 narrow gaps cut into it, and a screen on the far side to catch whatever comes through. That is the entire apparatus. A child could build a rough version of it in an afternoon. And that plain little arrangement, the plainest experiment in physics, contains a fact about reality that has never been comfortably explained, and that a great many serious, careful people suspect may never be. Richard Feynman, who understood quantum mechanics as well as anyone who has ever lived, used to tell his students that this single experiment holds the only real mystery of the whole theory. Not one mystery among many. The mystery. Everything strange about the quantum world, he said, everything that refuses to fit the way your mind wants the world to work, is already there in this one demonstration, waiting, if you are willing to look at it honestly. He was not being dramatic, he was being precise. He had spent his life inside the mathematics, and he was telling you where the strangeness actually lives. Tonight, I want to walk you through that experiment slowly, not quickly the way it usually gets told, with the surprising part rushed out in a single breathless sentence so the video can move on. I want to take the long way. I want to build it up piece by piece, the way it was actually discovered, so that when we arrive at the strange part, you feel it the way the physicists felt it, as the floor quietly giving way beneath something you had always assumed was solid ground. Let me tell you where we are going, so you can relax into the journey. We are going to start with something completely ordinary, something you already understand in your bones even if you have never named it. Then we are going to make one small, reasonable change to the experiment and watch it become strange. Then we are going to try to catch the strangeness in the act, the way any sensible person would, by simply looking more closely. And that is the moment when the whole thing turns, because the looking changes the answer. The experiment behaves one way when it is watched, and another way when it is not. And from there, we will follow the question as far down as it goes, into what is actually waving, into what a measurement even is, and finally into the honest, unfinished argument at the center of modern physics about whether the world out there is really there at all when nobody is checking. I want to be careful and fair with you the whole way, because this is a topic that attracts a great deal of nonsense. You have almost certainly heard some version of the claim that consciousness creates reality, that your mind reaches out and collapses the universe into being, that this experiment is the scientific proof behind manifesting your desires or thinking your way to a better life. We are going to deal with that idea directly. We are not going to sneer at it, because it grew out of something real that great physicists genuinely proposed. But we are also not going to let it stand where the evidence does not support it. By the end of tonight, you will be able to tell the difference between the astonishing thing this experiment actually shows and the comforting story that has been draped over it. And the real thing, I promise you, is stranger and quieter, and more worth your attention than any of the versions that get sold. So picture the setup again. A source on one side, a barrier in the middle with two thin parallel slits, like two narrow doorways standing side by side, and a screen behind the barrier to record where things land. If you send something through those two openings and look at the screen, what pattern do you expect to see? That question sounds trivial, and for most of the things in your daily life, the answer really is trivial. But the whole of what follows depends on getting clear about it first, because the surprise only means something once you know exactly what you were expecting instead. Think about throwing something solid through the two gaps. Imagine you had a paint gun, and you stood back and fired little balls of wet paint at the barrier, thousands of them, in every slightly different direction. Some aimed a bit left, some a bit right, some straight ahead. Most of them would splatter against the wall and go no further. But the ones that happened to be lined up with a slit would pass through and strike the screen behind. Where would the marks be? You already know without doing any mathematics. You would get two stripes on the screen, one behind each slit, because the paintballs travel in straight lines, and only the ones aimed roughly at an opening get through, and they carry straight on to the wall beyond. Two openings, two stripes. That is what particles do. That is what anything solid and definite does. Anything that travels as a compact little lump from one place to the next. Two slits give you two bands, brightest directly behind each gap and fading at the edges. Hold that picture. It is the picture of a world made of tiny bullets, and it is the picture your intuition trusts. Now I want you to hold a second picture beside it, because the entire experiment is a contest between these two pictures. The second picture is what happens when the thing you send through the slits is not a stream of little bullets, but a wave. And to understand what a wave does when it meets two openings, we do not need any exotic physics at all. We only need to remember something you have watched with your own eyes, probably many times, without ever thinking of it as physics. We need to think about what happens on the surface of water, because a wave, it turns out, does something at two slits that a bullet never could, and that difference is the seed of the whole mystery. It is the reason this simple little experiment stopped being simple and started keeping some of the smartest people alive awake at night. It is worth pausing on why Feynman singled this experiment out, because he had the entire strange menagerie of quantum physics to choose from. He could have pointed to entanglement, or to the uncertainty principle, or to the way particles seem to pop in and out of empty space. Instead, he kept returning to the two slits, and his reason was that everything else can, with enough effort, be talked around. You can tell yourself a story about uncertainty that makes it sound like ordinary ignorance. You can tell yourself a story about entanglement that makes it sound like ordinary correlation. But the double slit, done honestly, resists every such story. There is no way to describe what happens that does not, at some point, force you to say something your mind rejects. That is why he loved it as a teaching tool. It does not let you hide. It puts the impossibility right in front of you in the plainest possible terms, and dares you to explain it away, and you cannot. There is also a long human story behind those two slits, a debate that ran for centuries before anyone could settle it, and knowing it helps you feel why the stakes were so high. Isaac Newton, whose authority towered over physics for generations, believed light was made of tiny particles, little corpuscles streaming from luminous bodies. His rival Christian Huygens argued that light was a wave. For over 100 years, Newton's view mostly won, not because the evidence was decisive, but because Newton had said it. It took the stripes on a screen to break the deadlock, and even then the man who produced them faced ridicule for daring to contradict Newton. So when we send our first particle through the slits and watch it behave impossibly, we are not just doing a physics demonstration. We are standing at the end of a very old argument about what the world is made of, an argument that people assumed had been won, and we are about to watch it reopen in the strangest way imaginable, with the answer turning out to be, unbearably, both. So before we send anything quantum through those two doorways, Let me take you to the edge of a still pond and show you the thing that everybody already knows and almost nobody stops to marvel at. Part 2. The pattern that only waves can make. Imagine a calm pond at night, the surface perfectly flat, holding the reflection of the sky. You drop a single stone into it, and a ring spreads outward, a moving circle of raised water chasing itself away from the center. That ring is a wave. It is not water traveling across the pond, which is the first thing worth pausing on. The water itself mostly stays where it is, bobbing up and then down as the disturbance passes through it. What moves across the pond is the pattern, the up and down, the shape of the disturbance handed from one patch of water to the next. A wave is not a thing so much as a happening, a pattern of motion moving through a medium that itself stays home. Keep that in mind, because later, when we ask what is waving in the quantum world, the answer is going to be strange precisely because there is no pond. Now drop 2 stones into the pond at the same time, a little distance apart. 2 rings spread out, and very soon they reach each other and begin to overlap. And where they overlap, something orderly and beautiful happens. In some places, the crest of one ring arrives exactly together with the crest of the other. The 2 lifts of water add together, and you get a taller crest than either wave could make alone. In other places, the crest of one ring meets the trough of the other, the high point of one arriving exactly where the low point of the other is, and they cancel. The lift and the dip erase each other, and the water there barely moves at all. This adding and cancelling is called interference, and it is the signature of waves. It is the thing waves do that bullets cannot. Look closely at the overlap region, and you will see that these reinforcements and cancellations are not scattered at random. They lie along smooth curves, fanning out across the surface, lines of big motion alternating with lines of stillness, a fixed pattern, hanging in the water for as long as you keep making the waves. That steady arrangement of louder and quieter, of more and less, is what physicists call an interference pattern. And the crucial point, the point the whole experiment turns on, is that only waves make it. A stream of bullets cannot produce lines of perfect stillness sitting between lines of doubled impact. Bullets only ever add. 2 sources of bullets give you more bullets everywhere. It takes a wave with its crests and troughs, its capacity to cancel itself out, to carve those bands of nothing into the middle of all that motion. This is exactly what Thomas Young did with light at the very start of the 1800s, around 1801, and it settled an argument that had been running for over a century. People had wondered whether light was a stream of tiny particles, little corpuscles, as Newton had imagined, or whether it was a wave. Young sent light through 2 narrow slits and let it fall on a screen, and what appeared was not 2 bright lines. It was a row of many bright bands separated by dark ones, bright where the light waves from the 2 slits arrived in step and reinforced, dark where they arrived out of step and cancelled. That row of stripes, that interference pattern, was the fingerprint of a wave. There was no way to get bands of darkness between the slits out of little particles that only ever pile up. So light, everyone agreed, was a wave. The stripes proved it. For most of a century that was that. I want you to really sit with why those dark bands are so damning for the bullet picture, because it is easy to nod along and miss how strange it already is, even here, before any quantum mechanics arrives. In the dark bands, there is less light with both slits open than there would be with only one. Think about that. You open a second doorway for the light to come through, you add a whole second source of it, and certain spots on the screen go darker. If light were simply particles, more openings could only ever mean more light arriving everywhere, or, at worst, the same. Adding a source and getting less is something only cancellation can do, and only waves cancel. The darkness is the proof. Wherever you see a dark band, you are looking at a place where 2 contributions have met and annihilated each other, leaving stillness where each one alone would have brought brightness. So now we have our 2 clean, opposite pictures, and I want them both fixed firmly in your mind before we go any further, because everything that follows is the collision between them. Picture 1, bullets. Send little solid lumps through 2 slits and you get 2 stripes, one behind each slit, and opening a second slit only ever adds light. That is what particles do. Picture 2, waves. Send a wave through 2 slits and you get many stripes, an interference pattern with bands of perfect darkness where opening the second slit has somehow removed the light. That is what waves do. These are not subtle cousins. They are visibly, unmistakably different outcomes. If you were handed a screen and shown the pattern on it, you could tell in a single glance which one you were dealing with. 2 bands, particles. Many bands with darkness between them, waves. There is no ambiguity. The experiment sorts the world into 2 boxes, and for 200 years, everyone was confident they knew which box each thing belonged in. Light was a wave. That was the verdict of young Stripes, and it stood as settled science. Solid matter, the stuff of bullets and sand grains and everything you can hold, was made of particles. 2 different kinds of thing, 2 different boxes, 2 different patterns on the screen. Clean, comfortable. The kind of clarity physics is supposed to give you. Let me give you one more handle on why the interference pattern is so specific, so unfakeable, because it will matter when we try to explain it away later. The spacing of the bright and dark bands is not arbitrary. It is set by a simple geometric fact. Whether the 2 paths from the 2 slits to a given point on the screen differ in length by a whole number of wavelengths or by a half. Pick a point on the screen directly opposite the midpoint between the slits, and the 2 paths to it are equal in length, so the waves arrive perfectly in step, crest with crest, and you get a bright band. Move a little to the side, and one path grows slightly longer than the other. When that extra length reaches exactly half a wavelength, the crest of one wave lands on the trough of the other, and they cancel, and you get darkness. Move further, and when the extra length reaches a full wavelength, they are back in step, and you get brightness again. That is why the bands are evenly spaced, and why their spacing tells you the wavelength of whatever you sent through. The pattern is not a smear. It is a precise ruler laid down by the arithmetic of overlapping waves, and you can predict every band's position with a single line of geometry. This precision is exactly what makes it impossible to counterfeit with particles. Bullets have no wavelength, no crest and trough, nothing to add and cancel, and so they can never draw that ruler on the wall. Thomas Young, when he first showed this for light, was not celebrated for it. He was attacked. To suggest that the great Newton had been wrong about the nature of light was, in the England of his day, close to heresy, and Young was mocked in print for it. But the Stripes did not care about Newton's reputation. They were simply there, on the screen, undeniable, and slowly. Over the following decades, the wave picture of light won the argument on the strength of that one pattern, and the many experiments that built on it. By the middle of the 1800s, the matter seemed permanently closed. Light was a wave, full stop, and the double slit was the proof every student learned. Nobody suspected that the same little experiment, turned on matter and turned down to a single particle at a time, would one day reopen a question that everyone believed had been answered forever. And then, over the first decades of the 20th century, that clean division began to come apart from both ends. Light, the settled wave, started showing behavior that only made sense if it came in tiny, indivisible packets, little grains of energy that could knock electrons off a metal surface one at a time. The discovery that won Einstein his Nobel Prize. Light was somehow also grainy, also particle-like, and matter, the settled particles, started showing the opposite. Electrons, those tiny definite specks of stuff, began to hint that they too could behave like waves. Which raises the obvious, dangerous question, the one that turns our simple little experiment into the doorway of the whole mystery. What happens if you take the double-slit experiment, the very machine built to tell waves from particles, and you send through it something that is supposed to be a particle, one single electron, entirely alone? Which box does it fall into? Which pattern appears on the screen? Let me show you, because the answer is where the ground begins to move. Part 3. One particle, sent alone. Let us build the machine properly this time. Instead of light, we will use electrons because electrons are about as particle-like as anything gets. An electron has a definite mass. It has a definite electric charge, always the same amount, never half of it. You can catch a single one and hear it register as a single click on a detector. Nobody has ever caught half an electron. If anything in this world deserves to be called a tiny bullet, it is the electron. So we build an electron gun, a small device that fires electrons one at a time, and we aim it at a barrier with 2 slits, and behind the barrier we put a screen that lights up with a tiny flash wherever an electron strikes it. Then we turn the gun down as low as it will go, so low that only 1 electron crosses the apparatus every few seconds, with long empty stretches in between when nothing at all is in flight. This matters enormously. At any given moment, there is only 1 electron anywhere in the machine. There is no crowd. There is no second electron for it to bump into or interfere with. Each one makes its lonely trip through the barrier entirely by itself, and lands and flashes before the next one is even fired. At first, the screen tells a completely sensible story. An electron is fired, and a single bright dot appears somewhere on the screen. 1 dot, sharp and localized, exactly where a particle should land. Then another electron, another single dot, in a slightly different place. Then another. Each one arrives as an individual speck, a definite little hit at a definite little spot, precisely what you would expect from a tiny bullet. There is nothing wave-like about any single arrival. If you stopped the experiment after a few electrons, you would say, well, of course, electrons are particles. Look, they land as dots, one at a time, just like grains of sand thrown at a wall. And you would feel reassured, but you do not stop. You let it run. You sit and watch the dots accumulate. 1 every few seconds. Patient minute after patient minute. Hundreds of them, then thousands, each one landing at its own single spot, apparently scattered, apparently random. And as the count climbs into the thousands, and then the tens of thousands, something surfaces out of all those individual specks that should not be there. The dots are not evenly spread. They are not forming 2 simple bands behind the 2 slits. They are gathering into stripes. Bright rows where a great many electrons have landed, separated by rows where almost none have landed at all. Clean gaps that the dots have avoided. As more and more electrons arrive, the stripes sharpen, and there is no mistaking what they are. It is an interference pattern. It is the fingerprint of a wave. It is young stripes built 1 particle at a time out of thousands of separate, lonely, definite little arrivals. Stop and feel how impossible that is. Each electron went through the machine alone. There was never more than 1 in there at a time. So each electron could only have interfered with itself. But interference is a thing that happens between 2 waves passing through 2 openings. For a single electron to interfere with itself, that single electron would have had to pass through both slits at once, become 2 overlapping waves, and then meet itself on the far side to reinforce here and cancel there, before somehow gathering back into a single dot at the moment it struck the screen. 1 particle, 1 indivisible speck of matter that you can never cut in half, went through 2 doors at the same time. There is no gentler way to say it. The pattern on the screen cannot be built any other way, and the pattern is right there, plain as the stripes on a flag. Let me slow down here and take you inside it, because the words can slide past too easily. Imagine you are that electron. You leave the gun as a single, definite thing, launched into the darkness between the gun and the barrier. Ahead of you, somewhere in the black, stand the 2 openings, side by side. You do not swerve. You do not split down the middle like a droplet. And yet the question that feels so obvious, the only question that seems worth asking, the question which slit did you go through, turns out to have no answer. Not a hidden answer that the experiment is too clumsy to read. No answer at all. You did not go through the left one. You did not go through the right one. You did not go through one while secretly grazing the other. What arrives at the screen behaves as though the whole spread of your possible ways of getting there went out to meet the barrier, passed through both openings as a single expanding possibility, overlapped with itself in the dark, and only when you finally touched the screen did all of that collapse back down into one small, certain flash at one small, certain place. Between the gun and the screen, you were not a dot moving along a line. You were a wave of possibility, not a wave of stuff, a spread of everywhere you might land, and the machine let that spread interfere with itself before it ever asked you to be somewhere in particular. Stay inside that image a moment longer, because it is the truest picture of what a quantum thing is, and it will anchor everything that follows. You are used to thinking of yourself, and of every object, as a thing in a place, a definite bundle sitting at some spot, moving along some path. The electron between the gun and the screen is not that. It is not a tiny ball that we have merely lost track of. It is a shape of possibility filling the space ahead, thicker where it is more likely to be found, thinner where it is less, reaching through both openings at once, folding over itself, adding and cancelling with itself. And it is that whole spread, that entire cloud of maybe, that is the electron in flight. The single dot on the screen is not the electron finally revealing where it secretly was. The single dot is the electron becoming, for the first time, a thing in a place. At the instant, the screen asks it to be one. Before that instant, there was no place to reveal. There was only the spread, and the spread was real enough to interfere. This is the first crack in the floor, and I want you to notice that we have not done anything exotic to get here. We did not smash anything at enormous energy. We did not go to the edge of a black hole. We built a child's version of a physics demonstration and turned the source down low. And the most ordinary particle in the world stopped having a definite path. That is what unsettled everyone. The strangeness is not hiding in some far corner of the universe that you will never visit. It is in the electrons streaming through the screen you are looking at right now. It was always here. I want you to know that this is not a thought experiment. For a long time it was, because the technology to fire and detect single electrons cleanly did not exist, and even Feynman, when he described it in his famous lectures, presented it as an idealized demonstration that could only be imagined in perfect form. But it has since been done, for real, many times over. In 1961, a physicist named Klaus Jönsson produced genuine electron interference through multiple slits. And in 1989, a team led by Akira Tonomura, working at Hitachi in Japan, made the version that has become iconic, filming single electrons arriving one at a time on a screen and building, dot by patient dot, into the full interference pattern. You can watch that film. It exists. It begins as a scatter of what looks like random specks, and it ends as clean, unmistakable stripes. And there is nothing between the beginning and the end but thousands of individual electrons, each fired alone, each landing alone, each contributing one dot to a pattern that none of them could have known about. It is one of the most quietly astonishing pieces of footage in the history of science, and almost nobody outside physics has ever seen it. And it does not stop at electrons. This is the part that should genuinely unsettle you, because you might comfort yourself with the thought that electrons are tiny, ghostly, barely things, and that of course such wispy objects behave strangely. But physicists have pushed the experiment upward, to larger and larger objects, hunting for the place where the strangeness stops. They have done it with whole atoms. They have done it with small molecules. In 1999, a group in Vienna led by Marcus Arndt sent buckyballs through the apparatus, soccer ball-shaped molecules of 60 carbon atoms each, objects large enough that in a certain sense you could almost imagine seeing one. And the buckyballs interfered, went both ways, built the pattern. In the years since, the same group has done it with molecules of hundreds and then thousands of atoms. There is, so far, no upper limit where the wave behavior simply switches off. It just gets harder and harder to keep the object isolated enough to see. As far as anyone has been able to test, the rule that governed our single lonely electron governs everything all the way up, and the only reason your body does not visibly go through both slits is a practical matter of scale and isolation that we will come to. The strangeness is not a property of small things. It appears to be a property of all things, showing itself only when a thing is left truly alone. Now, if you are the kind of person who trusts your own eyes, you already know what you want to do next. You want to catch it. You want to stop taking the pattern's word for it and simply watch. Put a little detector right at the slits and see with your own instruments which opening each electron really goes through. Because surely, you think, the electron does go through one of them. Surely this talk of going through both is just our ignorance, and if we look carefully enough, we will catch the electron sneaking through the left slit or the right slit, like anything sensible would, and the mystery will dissolve. It is exactly the right instinct. It is what every good physicist wanted to do. So let us do it. Let us look, and let me show you what happens to the pattern the moment we do, because that is where the crack becomes a chasm. Part 4. The question that kills the pattern. So we add a watcher at the slits. Right at each opening we place a small detector, some device that can register the passage of an electron and tell us, for every single one, whether it went left or right. Nothing else about the experiment changes. Same gun, same 2 slits, same screen, same slow trickle of one electron at a time. The only new thing is that now we are keeping a record of the path. Now, at last, we will know which way each electron went. And then we let it run, and we watch 2 things at once. We watch the little detectors report left, right, right, a clean record building up, each electron caught going through exactly one opening like the particle it is. And we watch the pattern building on the screen behind. The pattern is gone, not blurred, not weakened. Gone, replaced by something else entirely. On the screen there are now 2 bands, one behind each slit, brightest directly behind the openings and fading at the edges. Exactly the pattern you would get from tiny bullets. The stripes, the interference, the bands of impossible darkness, all of it has vanished the moment we started recording which slit each electron used. We looked, and the electrons stopped going through both doors. Now each one goes through one door, cleanly, like a sensible particle, and lands in one of 2 simple heaps. The wave behavior is nowhere to be found. And then, because you do not quite believe it, you turn the detectors off again. You stop recording the path. You change nothing else at all, and the stripes come back. Slowly, dot by dot, the interference pattern reassembles itself on the screen. The bands of darkness returning to the exact places they had abandoned. Turn the watching on, and the electrons behave like particles that went through one slit. Turn the watching off, and they behave like waves that went through both. The screen answers to whether or not you are keeping the record. The behavior of matter depends on whether the path is known. Let me put you at the machine, because this is a thing you should feel and not just be told. You are standing in a darkened room. In front of you, the screen is alive with the faint building of stripes, the interference pattern glowing there, band after band of light and dark, the fingerprint of a wave. Under your right hand there is a switch, and that switch turns on the little detectors at the slits, the ones that will tell you which way each electron goes. You press it. There is no sound, no jolt, nothing you can feel. But on the screen in front of you, the stripes begin to dissolve, the dark bands filling in with dots that were never allowed there before, the whole delicate pattern softening and smearing until it settles into 2 dull heaps of light, one behind each slit. You lift your finger off the switch, you wait, and the stripes bleed back into being, the dark bands clearing themselves out again, the pattern reassembling as though it had only been holding its breath. Down goes your finger, and reality is made of particles with definite paths. Up goes your finger, and reality is made of waves of possibility that went everywhere at once. A law of the universe, answering to a switch beneath your hand. Now the first thing any honest person wants to say here, and it is the right thing to say, is surely the detector is just bumping the electron. Surely to detect the electron, you have to interact with it. shine something on it, bounce a particle off it, and that interaction shoves the delicate little thing off course and smears out the pattern. That would be a completely ordinary explanation. It would mean the mystery is nothing more than clumsiness, the unavoidable fact that to measure a tiny thing you have to disturb it. And for a while that was a serious and respectable position. Even Heisenberg leaned on that kind of picture at first, the idea that the very act of measuring kicks the thing you measure. But the experiments did not let that comfort survive. Physicists spent decades designing gentler and gentler ways of learning the path, methods that extract which slit information, while depositing almost no push, almost no energy, almost no disturbance on the electron at all. They built what are called quantum eraser experiments, where the path information is written down not by slamming into the particle, but by quietly tagging some other property that comes along for free. And the result was always the same, and it was worse than clumsiness. The pattern died whenever the path became knowable, no matter how gentle the knowing was. And then came the part that truly broke the disturbance story. If you took that path information, already recorded, and you erased it before anyone read it, genuinely scrambled it, so that the universe no longer held any usable record of which way the electron went, the interference pattern came back. The very same electrons, already through the slits, already landed, would show stripes or no stripes in the final data depending on whether the record of their path was, in the end, preserved or destroyed. Sit with what that means, because it is the pivot of the entire night. It is not the pushing that kills the pattern. It is the knowing. It is not whether the electron got jostled. It is whether the information about which path it took exists anywhere in the universe in a form that could, even in principle, be read. When no such record exists, the electron travels as a spread of possibility through both slits and interferes with itself. When such a record does exist, the electron travels as a particle down one definite path. The dividing line between the two utterly different behaviors is not force. It is information. The universe seems to lay down the interference pattern only when it keeps no record of the path. The universe keeps no record, and reality stays a wave. The universe keeps a record, and reality becomes a fact. There is a way to make the trade-off precise, and I think the precision is worth a moment, because it shows this is real physics and not hand-waving. In the 1990s, physicists including Berthold Georg Englert, Marlon Scully, and their colleagues worked out an exact relationship between how much you can know about the path and how strong the interference can be. They defined a measure of how sharply the pattern shows, called the visibility, and a measure of how much which-way information is available, called the distinguishability. And they proved that these two quantities are bound together by a strict mathematical ceiling. Square the visibility, square the distinguishability, add them, and the sum can never exceed 1. That single inequality captures the whole tension in one line. If you have perfect path knowledge, the distinguishability is 1, so the visibility must be 0, and the stripes are completely gone. If you have perfect stripes, the visibility is 1, so the distinguishability must be 0, and you can know nothing about the path. And everything in between trades off smoothly. You can have a little path information and slightly washed out stripes, and the amounts are locked to each other by that equation. This is not a vague tendency. It is a law as sharp as any in physics, and it says that path knowledge and interference are two faces of one quantity that nature will not let you have in full at the same time. And this is exactly what rules out the comfortable explanation, the one where the detector just clumsily jostles the electron. If the effect were about physical disturbance, then a gentler detector should give you both, some path information and some interference, without any strict ceiling, and the ceiling would just depend on how careful your engineering was. But the ceiling does not depend on your engineering. It is fixed by the mathematics of the theory itself, no matter how gentle you make the measurement, and it is honoured to the last decimal in every experiment. The most delicate possible measurement of the path, one that deposits essentially no push at all on the electron, still destroys exactly as much interference as the equation demands, because it is the information, not the disturbance, that the equation is counting. This is the quiet, rigorous heart of why the mystery cannot be dissolved into mere clumsiness, and why physicists were forced, against every instinct, to take the role of knowledge in the physical world seriously. That is a sentence about physics that sounds like a sentence about metaphysics, and that is precisely why this experiment has never let anyone rest. It drags the question of what is known, and by whom, and whether it is written down anywhere, right into the machinery of what actually happens to matter. And once you have seen that, you cannot unsee it, and you are forced to ask the next question, the one that we have been circling since the first minute. If the electron between the slits is not a dot on a path, if it is this spread-out wave of possibility, then what is that wave? What exactly is waving? It is not water, it is not air. There is no pond. So what is the thing that goes through both slits, and what is it made of, and where does it live? That is where we go next, and I will warn you gently in advance, the answer does not make the world more solid. It makes it stranger. But it makes it stranger in a way that, once you see it, is almost unbearably elegant. Part 5. What is actually waving? When physicists worked out the mathematics that describes the electron between the gun and the screen, they found that they could account for everything: the stripes, the single dots, the way the pattern lives or dies with the record, by assigning to the electron a kind of spread-out mathematical wave. It is usually written with the Greek letter psi, and it is called the wave function. The wave function is not centered on a single point the way a particle is. It is smeared across space, larger here, smaller there, and when it reaches the barrier, it passes through both slits and overlaps with itself on the far side, exactly the way the ripples on the pond overlapped. Where the two parts of the wave function reinforce, the electron is very likely to land. Where they cancel, the electron is almost never found. Run the mathematics, and out comes the interference pattern, precisely. Band for band. The wave function works. It is one of the most successful pieces of description in the history of science. There is only one small problem, and it is the problem that has kept the argument alive for 100 years. Nobody can agree on what the wave function actually is. Here is what makes it so slippery. The wave on the pond is a wave of water. The sound wave in the air is a wave of pressure, of air molecules crowding and thinning. Every ordinary wave is a wave in some substance, a pattern of something physical moving up and down. But the wave function is not a wave in any substance. There is no material being displaced. When Max Born worked out in 1926 how to connect the wave function to what you actually see, he found that the wave does not tell you how much electron is at each place. It tells you the probability of finding the whole electron there if you look. More precisely, you take the height of the wave at a given point, and you square it, and that gives you the chance of the electron turning up at that spot. That rule, that the square of the wave function gives the probability, is called the Born rule, and it is the bridge between the smooth mathematical wave and the sharp single dots on the screen. The bright stripes are where the squared wave is large, so many electrons land. The dark stripes are where the squared wave is near zero, so almost none do. So the thing that goes through both slits, the thing that waves, is not a substance at all. It is possibility itself given a precise mathematical shape. It is a wave of where the electron might be, a wave of possibility, not a wave of stuff. And that spread of possibility is every bit as real as it needs to be to interfere with itself, to create bands of genuine darkness where two possibilities cancel, to build the pattern out of nothing but chances. The electron between being fired and being found does not have a position that we happen not to know. It has no single position at all. It has a wave function, a spread, and the position only comes into existence, one definite value out of all the possibilities at the moment it is measured. There is a deep puzzle hiding even in this bridge between the wave and the dot, and it is worth naming, because it is one of the things that keeps physicists honest about how little they truly understand. The Born rule, the recipe that says, square the wave function to get the probability, works flawlessly. It has never once failed, and yet nobody can derive it from anything more basic. It sits in the theory as an extra assumption, bolted on beside the smooth equation, and when you ask why probability should be the square of the wave, rather than, say, the wave itself or its cube, the honest answer is that we know it must be so because it matches every experiment, not because we can show it follows from deeper principles. Some of the interpretations we will meet later spend most of their effort trying to explain where the Born rule comes from, and none has fully convinced the others. So even the simple act of translating the spread of possibility into a bettable chance conceals a mystery. The most tested numerical rule in all of physics is, at bottom, a fact we take on the authority of nature, not one we can yet explain. There is also something worth saying about what the probability is a probability of, because it is not what you might assume. It is tempting to think the wave function gives the chance that the electron is already at some spot, and we simply have not looked yet. But that is exactly the reading the interference pattern forbids. If the electron already had a definite position before we measured, then it went through one slit or the other, and there would be no way for the two possibilities to overlap and cancel, and the dark bands could not exist. The dark bands prove that the possibilities were all genuinely present and interfering, right up until the measurement. So the probability is not the chance of finding something that was already there. It is the chance that a definite position, which did not exist before, will come into being here rather than there when the measurement is made. That is a far stranger kind of probability than the odds on a coin already lying hidden under a cup, and keeping the difference clear is the whole key to not fooling yourself about what this experiment shows. This condition of being spread across many possibilities at once has a name, and you have almost certainly heard it, usually used loosely. The name is superposition. A quantum system in superposition is not in one state or another with us merely ignorant of which. It is genuinely in a combination of states at the same time, and the combination is real because the different parts of it can interfere with one another, and interference is something only real. Coexisting things can do. The electron at the slits is in a superposition of going through the left and going through the right. Both possibilities are present, both are contributing, and their overlap is what carves the stripes. Superposition is not a fancy word for uncertainty. Uncertainty is when there is a fact you do not know. Superposition is when there is no single fact yet to know. I want to guard you against a misunderstanding that trips almost everyone, because getting it right is what keeps this from sliding into nonsense later. Superposition does not mean the electron is in two places in the ordinary sense, as if there were two little electrons, one at each slit, that you could photograph. If you actually go and look at the slits, you never find two electrons, and you never find half of one at each. You always find one whole electron at one place. Superposition is the condition before you look, the condition of the possibilities themselves, the spread that has not yet been asked to become a fact. The instant you ask, by measuring, you get one whole answer. What superposition tells you is that in between the asking, the different answers are all genuinely live, and they can touch each other and add and cancel, which is why the pattern appears. The two-ness is in the possibilities, not in the particle. Now you can state the mystery with real precision, and it is worth doing, because a well-stated mystery is halfway to being understood. Between measurements, a quantum system is described by a wave function that spreads smoothly, obeys an exact and beautiful equation, and can hold many possibilities in superposition at once, all of them real enough to interfere. But every time you actually measure the system, you do not find a spread, you find one definite outcome, one dot, one slit, one value, chosen with probabilities set by the square of the wave. The smooth spreading wave and the single sharp result are two completely different kinds of behavior, and the theory, for all its precision, does not contain any rule that says when one turns into the other. The equation that governs the wave function describes only the smooth spreading. It never, on its own, produces a single outcome. That final step from a wave of many possibilities to one actual event has to be put in by hand, by us, every single time we compare the theory to what we see. We know the world takes that step because we see single dots. We simply cannot say, from within the theory, what takes it, or when, or how. Let me add one more layer to what the wave function is, because there is a detail that makes it even stranger and even more clearly not a wave of any ordinary substance. The height of the wave function at each point is not an ordinary number. It is what mathematicians call a complex number, a number with two parts, which you can picture as having both a size and a direction, like the hand of a clock that can point any way. When two parts of the wave function meet, you do not simply add their sizes. You add these little clock hands, taking their directions into account, and that is precisely what allows cancellation. Two clock hands of the same size, pointing in opposite directions, add up to nothing, and that nothing is the dark band on the screen. Then, to get the actual probability, you take the length of the resulting combined hand and square it. This is why the Born rule squares the wave function, and why interference is possible at all. The particle's possibilities do not just have amounts. They have these hidden directions, these phases, and the phases can align to reinforce or oppose to cancel. There is nothing in the everyday world that is quite like this. It is not a wave of water, and it is not even a wave of simple probability. It is a wave of these two-part quantities whose directions can erase one another, and only after they combine do you square the result to get a chance you could actually bet on. And here is the feature that sharpens the coming mystery to a point. The equation that governs how this wave function changes over time, the Schrödinger equation, is completely smooth, completely continuous, and completely deterministic. Give it the wave function now, and it tells you the wave function at every future moment, with total certainty, no randomness anywhere, the possibilities flowing and spreading and interfering in a perfectly lawful, predictable dance. There is no chance in it at all. The randomness, the single, unpredictable dot, the probabilities from the Born rule, none of that is anywhere in the equation that describes the wave's evolution. It appears only at the moment of measurement, the moment the smooth, deterministic wave is somehow replaced by one sharp, random outcome. So the theory has two completely different modes, and they could not be more opposed. Between measurements, smooth, lawful, deterministic, reversible spreading. At a measurement, sudden, random, irreversible collapse to a single value. And nothing in the theory says when to switch from the first mode to the second. We just know from what we see that the switch happens. That gap has a name too, and it is the true subject of tonight, the thing all the strangeness has been leading toward. It is called the measurement problem. It is not a problem of clumsy instruments or missing data. It is a hole at the center of the most successful theory ever written, a place where the mathematics hands off to a step it does not describe. The wave spreads according to the law. The outcome appears according to nothing the law contains. And into that gap, that silence where the theory says nothing about the most important moment, physicists have poured 100 years of competing stories about what is really happening. Stories that agree on every number and disagree on the nature of reality itself. Before we walk through those stories, I want to make you feel the full size of the gap, because everything hangs on it. So let me show you the measurement problem in its purest and most disturbing form, dragged out of the world of electrons and into a room with a cat. Part 6. The problem at the center of everything. Erwin Schrödinger, who wrote the very equation that governs how the wave function spreads, was deeply uneasy about what his own mathematics seemed to imply. So in 1935, he built a thought experiment designed to make the discomfort impossible to ignore, and it has been troubling people ever since. Picture a sealed steel box. Inside it, there is a single radioactive atom, the kind of quantum system we have been discussing, a thing that lives in superposition. In any given hour, that atom has some chance of decaying and some chance of not decaying, and until it is measured, the mathematics says it is in a superposition of both, decayed and not decayed at once, exactly like the electron going through both slits. So far, this is just a quantum atom doing an ordinary quantum thing. Now Schrödinger connected that atom to the everyday world. Inside the box, he placed a detector that watches the atom, and if the atom decays, the detector triggers a hammer, and the hammer breaks a small flask of poison, and the poison kills a cat that is also sealed in the box. If the atom does not decay, nothing happens, and the cat is fine. Everything in the chain is rigidly linked. The atom's fate decides the detectors decides the hammers decides the flasks decides the cats. And here is the knife. If the atom is genuinely in a superposition of decayed and not decayed, and every link faithfully passes that superposition along, then by the same mathematics that gives us the interference pattern, the cat must end up in a superposition of dead and alive. Not hidden, not merely unknown to us. Actually both, in the way the electron actually went through both slits, until someone opens the box and looks. Nobody believes there are cats that are literally both alive and dead. That is Schrödinger's whole point. He was not proposing it as a real state of affairs. He was using the cat as a blade to expose the gap. The mathematics of superposition, applied honestly and without any special exception, marches straight up the chain from the atom to the cat and insists the cat should be smeared across both outcomes. Our experience insists it is not. The cat is one thing or the other before the box is ever opened. So somewhere between the single atom and the whole cat, the superposition must have stopped, must have turned into one definite fact. And the theory does not say where. That is the measurement problem, standing in daylight. Where is the line? Where does the smooth spreading wave of many possibilities become a single actual event? At the atom? At the detector? At the hammer? At the cat's own eye? At the human who opens the box? The equation is silent. It describes the spreading beautifully and says nothing about where the spreading is allowed to stop. The mathematician John von Neumann studied this chain with total rigor and found something that only deepened the unease. No matter where you try to place the boundary, the point at which the quantum haze becomes a classical fact, the mathematics lets you push it further along without any contradiction. You can say the detector made it definite, but you can equally well describe the detector itself with a wave function in superposition, and then it is the hammer that must decide. And you can describe the hammer that way too, and then it is the cat, and then the eye, and then the brain of the observer. This sliding boundary is sometimes called the von Neumann chain, or the Heisenberg cut. And the disturbing thing is that the theory places it nowhere in particular. It floats. You, the physicist, put it wherever you need it to make the sums come out, and the sums always come out, no matter where you put it. The theory works flawlessly and tells you nothing about the one thing you most want to know, which is what, in the actual world, actually turns a possibility into a happening. Here is the quiet center of everything I want you to take from tonight, and I am going to say it slowly. The equations of quantum mechanics never tell you when a possibility becomes an event. They describe the growing, spreading, interfering wave of what might happen with perfect precision. The most precise predictions in the history of science, confirmed to more decimal places than anything else humans have ever tested. And then, at the decisive instant, the moment when the world stops offering possibilities and delivers one solid fact, the equations fall silent. We add that step ourselves, by hand, every time, because we can plainly see that the world does it. We open the box and the cat is one thing. We look at the screen and there is one dot. The world takes the step. We just cannot find, anywhere in our best description of reality, the thing that takes it. We have written down the laws of the universe with a blank space at the very moment that matters most, and we have been filling in that blank by hand for 100 years without ever learning what belongs there. I think it helps to say plainly what kind of not knowing this is, because there are two very different kinds, and they are easy to confuse. There is the ordinary not knowing of a fact that exists, but is hidden from us, like the number of grains of sand on a beach, which is some definite number we simply have not counted. Almost all of science deals with that kind, and it yields to better instruments and more careful work. And then there is a stranger not knowing, the not knowing of something that does not yet have a definite value to be known, where the missing answer is missing not from our records, but from reality itself. The measurement problem is the second kind. When we say we do not know what turns a possibility into an event, we do not mean there is a mechanism sitting there that we have failed to detect, though there might be. We mean that our complete, flawless, endlessly confirmed theory contains no such mechanism at all, and that the world nonetheless produces definite events, and we cannot close the gap between those two facts. It is not that the answer is written somewhere we cannot reach. It is that our best description of the universe has a shape in it exactly where the answer should be, and the shape is empty. That is not a small confession. Consider how it compares to every other thing you were taught about the physical world. You were taught that the world runs on laws, that if you knew the state of things and the rules, you could in principle say what happens next. That is the promise physics made ever since Newton, and mostly it has kept it. But right here at the foundation, in the plainest experiment in physics, that promise runs out. The rules describe the possibilities and then decline to say which one occurs, or why this one and not that one, or what event out in the world corresponds to the moment of choosing. Every single dot on that screen is an event that the deepest theory we possess did not predict and cannot explain the occurring of. It predicts only how often, across many trials, each spot gets chosen. The individual choice, the actual single happening, is something the universe does and the theory watches without comprehension. It is worth sitting for a moment longer with just how deliberately strange Schrödinger was being, because the strangeness was the whole point, and it is easy to miss. He was not a mystic. He was one of the founders of the theory, the author of its central equation, and he built the cat precisely because he found the implication absurd and wanted to force his colleagues to confront the absurdity rather than paper over it. He was saying, in effect, look what your own mathematics commits you to if you apply it consistently. You are happy to let a single atom sit in a superposition of decayed and not decayed, because you cannot see the atom and it does not offend your intuition. But the atom is chained to a cat, and the same mathematics that keeps the atom in superposition must, if it is truly universal, keep the cat in superposition too. Either the mathematics stops being universal somewhere between the atom and the cat, in which case tell me exactly where and why, or you must accept a cat that is genuinely both alive and dead until observed, which no one believes. He was not offering a solution. He was refusing to let anyone pretend there was not a problem, and a century later nobody has closed the gap he pried open. And notice that the gap gets worse the harder you look at it, not better, which is the mark of a real problem rather than a temporary confusion. You might hope that the detector, being a large classical object, simply is where the collapse happens, that quantum rules apply to atoms, and classical rules take over for anything as big as a Geiger counter. But there is no line in the theory that says so. The detector is made of atoms, every one of them quantum, and if each atom obeys the wave equation, then the whole detector, being nothing but those atoms, must obey it too, and so it must be describable as a superposition, and then it cannot be the thing that ends the superposition. The same argument runs up through the hammer, the flask, the cat, the eye, the optic nerve, the brain. At no point does the theory hand you a natural stopping place. Everything physical is made of the quantum stuff, so everything physical should inherit the quantum haze, and the definite world we actually experience becomes the one thing the theory cannot deliver. That is the measurement problem in its full, uncomfortable depth. It is not that we lack a detail, it is that our most successful theory, applied without exception, predicts a world of endless superposition that looks nothing like the world we live in, and we have never found the principled place where the one becomes the other. And so we are left with a genuine fork, a real and unavoidable question that will not go away no matter how much we would like it to. Either there is some physical process, not yet in our equations, that genuinely collapses the spread of possibilities into one fact, a real event out there in the world that we simply have not finished describing. Or the collapse is not a physical event at all, but something about knowledge, about information, about the relationship between a system and whoever or whatever comes to know its state. Or, most radically, the collapse never happens at all, and all the possibilities go on being real, and it only seems to us that one was chosen. Each of those is a serious answer held by serious physicists. Each of them keeps the flawless mathematics exactly as it is, and disagrees only about what the mathematics means. And one of them, the family of answers, that ties the appearance of a definite fact to the act of measurement itself, is where the title's unsettling claim comes from, that reality does not fully exist until it is looked at. Before we can judge whether that claim deserves to be taken seriously, we have to look at the single strangest version of the experiment ever performed, the one that seems to let you reach back and change what a particle already did. Let me take you into the delayed choice. Part 7. The choice that comes too late. John Archibald Wheeler, one of the great physicists of the 20th century, and the man who popularized the term black hole, asked a question in the 1970s that sounds like a trick and is not. We have seen that if you know the path, you get particles and no stripes, and if you do not know the path, you get waves and stripes. Wheeler asked, what if we wait? What if we let the particle pass the slits first, get it well on its way toward the screen, and only then, at the last possible instant, decide whether or not we are going to find out which path it took? The particle has already gone through. Whatever it did at the slits, it did in the past. Surely by the time it is halfway to the screen, it has already committed, already been either a wave that went both ways, or a particle that went one way. Surely our late decision cannot reach back and change what already happened. The experiment has been done in careful and rigorous forms, most famously by Alain Aspect and his colleagues in France in 2007, using single photons and fast optical switches that make the choice after the light is already inside the apparatus. And the result is that it does not matter when you decide. If you choose, even at the last instant, to set things up so the path is knowable, you get particle behavior, no interference, as though the photon had gone one way all along. If you choose, at that same last instant, to set things up so the path is erased and unknowable, you get wave behavior, interference, as though the photon had gone both ways all along. The photon's past seems to arrange itself to match the choice you make after it should already be over. The behavior at the slits is not settled at the slits. It stays open, in some accounting sense, until the question of whether the path is known is finally closed, and that can happen long after the particle has flown by. I want to be very careful here, because this is exactly the kind of result that gets stretched into things it does not say. Nothing travels backward in time. No signal is sent into the past. You cannot use this to change history or send a message to yesterday, and every attempt to build such a thing out of it fails, for reasons that are precise and provable. The universe's books always balance, and no information ever moves backward. What the delayed choice destroys is not causality. What it destroys is the innocent picture in which the photon quietly decided at the slits, wave, or particle, and merely waited for us to catch up and discover the decision it had already made. That picture is dead. There was no decision at the slits waiting to be uncovered. The photon between the slits and the screen was not a thing with a definite hidden history. It was, again, a spread of possibility, and the possibility stayed genuinely open until the whole experimental question was finished, including parts of the question that we had not yet answered when the photon passed the barrier. Let me set you inside that impossible feeling moment, because it is one thing to hear it and another to stand in it. Imagine the photon has left the source. It has passed the region of the two paths. It is now in flight, somewhere in the dark between the slits and the screen, and by every instinct you have, whatever it was going to be, it already is. And only now, with the photon already past the fork, do you reach out and make your choice. You can slide a piece of apparatus into place that will make the two paths recombine and reveal an interference pattern, treating the photon as a wave that took both ways. Or you can leave it out, so that the path stays readable and the photon lands as a particle that took one way. The photon is already flying. Its trip through the fork is already, by any ordinary reckoning, in the past. And yet the pattern that forms, the record of what that photon was, waits on the movement of your hand right now, on a choice you have not yet made about a journey the photon has already taken. The past sits there not quite written, holding its shape open until you finish deciding what question you are asking of it. And when you decide, the past obligingly turns out to have always been consistent with your choice. There was never a moment you could catch it changing. There was only ever a past that refused to be definite until the present asked it to be. The quantum eraser makes the same point from another angle and hammers it home. In these experiments, the path information is recorded onto some companion particle, entangled with the one going through the slits, so that in principle you could read off which way it went. As long as that record exists and is readable, no interference appears. But then you take the companion particle and you measure it in a way that scrambles the path information beyond any recovery, erasing which-way knowledge from the universe entirely. And when you go back and sort the original particles according to the erased measurements, the interference pattern is there in the data, recoverable, even though those original particles landed long ago. The stripes come back not because you pushed anything, but because you destroyed the record. It is the knowing, once again, and only the knowing. When the universe holds a readable record of the path, reality is grainy and definite. When the universe keeps no record, reality is a wave of open possibility. And astonishingly, whether the record survives can be decided after the particle has already arrived. Wheeler had a way of dramatizing this that stretches it to a scale that should make your skin prickle. And it is not just a story, because a version of it has actually been carried out. Imagine, he said, that instead of a laboratory bench, our two paths are formed by a distant galaxy, whose gravity bends the light of a far more distant quasar around both sides of it, so that the quasar's light can reach us by two different routes through space, like light through two slits, except that the slits are separated by thousands of light years, and the journey has taken billions of years. Now, tonight, here on Earth, we choose how to set up our telescope. We can combine the two paths and look for interference, treating the ancient light as a wave that came both ways around the galaxy. Or we can set it up to determine which side of the galaxy each photon passed, treating it as a particle that took one route. And by Wheeler's argument, that choice made tonight seems to reach back across billions of years and determine whether that ancient light behaved as a wave taking both paths or a particle taking one, when it passed the galaxy long before the Earth or the Sun even existed. Laboratory versions of this cosmic delayed choice have been performed, and they behave exactly as the theory predicts. The decision we make now is entangled with what the light was then, in a way that shatters the idea that the light's history was a finished thing waiting for us to read. Let me be clear once more. because the temptation to overreach is strongest right here. Nothing in this reaches back and rewrites a fact that was already settled. The point is subtler and, once you sit with it, more disturbing than time travel. The point is that the light's behavior at the galaxy was never a settled fact in the first place, not until the whole chain of measurement was complete, including the part we only finished tonight. There was no hidden answer in the past that our choice altered. There was, in some precise accounting, no answer in the past at all, only a spread of possibility that stayed genuinely open until the present closed it. That is what the experiment forces on us. Not that we change the past, but that the past, in its fine quantum detail, may not be fully definite until it is measured, even if the measuring happens eons later. The universe keeps no record, and the question stays open. A record is finally made, and only then does the past become the particular way it always turns out to have been. This is the experimental heartbeat of the title's claim. It is not that a mind reaches out and paints the world into being. It is subtler and, honestly, stranger than that. It is that the definite, particular, this not that character of the world, the very quality of being one specific way, rather than a spread of ways, appears to be bound up with whether a measurement is made and a record is kept, and that binding does not respect the neat ordering of before and after that our intuitions demand. The world does not seem to carry a full set of definite facts about itself at all times, waiting to be discovered. It seems to settle its facts in the act of being measured and to leave them open, genuinely open, when they are not. Whether you call that reality not existing until you look depends entirely on what you are willing to mean by exist, and that, at last, is a question we can no longer put off. It is time to ask the most dangerous question in the whole subject, the one that separates careful physics from comforting fantasy. Does the universe need someone to watch it? Does it need a mind? Let us walk into that carefully, because it is where the real thinking has to be done. Part 8. Does the universe need a watcher? The idea that consciousness is what collapses the wave function has a real and respectable origin, and I want to give it its due before I tell you why most physicists have set it aside. When von Neumann studied that sliding boundary, the point where the quantum haze must become a classical fact, he showed that the mathematics lets you place it anywhere along the chain. Eugene Wigner, another brilliant physicist and a Nobel laureate, took that freedom and made a bold suggestion. Since the boundary can go anywhere, and since everything physical, the detector, the hammer, the cat, the eye, the brain, can itself be described by a wave function and folded into the superposition. Perhaps the one thing that cannot be so described, the one thing that finally forces a definite outcome, is conscious awareness itself. Perhaps the chain of possibilities runs all the way up until it reaches a mind, and the mind, being something the equations cannot swallow, is where the possibilities become an actual experience of one result. That is the serious version of consciousness causes collapse. It was proposed by first-rate thinkers wrestling honestly with a real gap, and it should be treated with respect. But respect does not mean acceptance, and the modern understanding has moved away from it, for a reason that is worth understanding, rather than just asserting. The reason is a process called decoherence, and it is probably the most important idea for making peace with the double slit that the 20th century produced. Decoherence is what happens when a quantum system in superposition stops being isolated and starts touching the rest of the world. Remember that the interference pattern, the living proof of superposition, survives only when the universe keeps no record of the path. The moment the electron's path gets entangled with anything else, anything at all that carries away information about which way it went, the interference between the possibilities becomes unrecoverable. And here is the point that dissolves the need for a conscious watcher. That entangling something does not have to be a person or a mind or even a deliberate detector. It can be a single stray photon bouncing off the electron. It can be one air molecule colliding with it. It can be a passing whisper of heat. Anything that interacts with the system in a way that records its state, and the environment is full of such things, everywhere, constantly, is enough to destroy the delicate superposition and leave behind something that behaves, for all practical purposes, like a definite classical fact. This is why you never see a coffee cup in two places, and why Schrödinger's cat is never really smeared across life and death. A cat is warm. It is enormous by quantum standards, made of countless particles, in constant contact with air, light, and its own body heat. Trillions upon trillions of interactions are recording its state every instant. Any superposition of a whole cat would be shattered by the environment so fast, so overwhelmingly, that it could never persist long enough for anyone to open a box and find it. The bigger and warmer and more connected a thing is, the more relentlessly the environment measures it, and the more instantly any quantum haziness is converted into ordinary definite facts. Decoherence explains, quantitatively, with real numbers, why the small world shimmers with superposition, and the large world stands solid and definite, and it does the whole job without any mention of minds, awareness, or observation in the human sense. The universe measures itself constantly, with rocks and photons and air, and no one has to be watching. So when a physicist says observer, this is what the word means, and it is crucial that you hear it correctly, because almost every popular distortion lives in this single misunderstanding. An observer, in quantum mechanics, is not a conscious being. It is any physical system that interacts with the quantum system in a way that records information about its state. A Geiger counter is an observer. A cold metal plate is an observer. A single photon flying off into space carrying the imprint of where the electron was is an observer. The word was a poor choice, a piece of unfortunate vocabulary from the early days that has fueled a century of mysticism. But its technical meaning has nothing to do with mind. The measurement that collapses the pattern is not an act of looking with eyes. It is an act of interacting in a way that leaves a trace. The universe was performing these measurements on itself for billions of years, before there were any eyes to look, and it will go on performing them long after. This is the point where I have to be direct with you, gently but plainly, about the version of this idea you have probably been sold. You have likely heard that the double-slit experiment proves consciousness creates reality, that your mind literally shapes the physical world, that quantum mechanics is the science behind manifesting wealth or love or health by thinking about it correctly. That observation in the quantum sense means your attention molds the universe to your desires. Every part of that is a misreading of the word observer. The experiments do not show that a human mind is required. They show that a physical record is required, and a puff of gas can make one. There is no evidence, none, that focusing your thoughts collapses wave functions in your favor, or that the universe is waiting on your attention to decide what to become. The electron does not care whether a person is in the room. It cares only whether its path has become entangled with anything that records it, and the room, the air, the walls, and the detector are all recording constantly, person or no person. The beautiful real strangeness of this experiment has been hollowed out and refilled with a flattering story that tells you that you are the center of the universe. The real result is stranger and more humbling than that, and it does not put you in charge of anything. The numbers behind decoherence are staggering, and they are worth hearing, because they turn the vague phrase measured by the environment into something concrete. Physicists have estimated how quickly a superposition of an everyday-sized object would be destroyed by ordinary surroundings, and the timescales are almost beyond imagining in their smallness. A dust grain floating in the air, if it were somehow placed in a superposition of two positions a hair's width apart, would be measured back into definiteness by the air molecules around it in a time so short that light itself would barely have crossed a single atom. Even in the emptiness of space, the faint background glow left over from the birth of the universe, The cosmic microwave background, that whisper of radiation filling all of space, would be enough to collapse the superposition of a good-sized speck of dust in a fraction of a second. There is essentially nowhere in the universe quiet enough and cold enough and empty enough to let a large object hold a superposition long enough to notice. The environment is always watching, everywhere, and it watches large things vastly faster than it watches small ones, because a large thing disturbs vastly more of its surroundings. This is why the boundary between the shimmering quantum world and the solid classical one is not a sharp line at some particular size, but a smooth, ferociously steep slope, and it is set entirely by how strongly a thing talks to its surroundings. It also explains something that might have been nagging at you. If superposition is everywhere, why did it take until the 20th century for anyone to notice it? And why do we have to build such delicate, isolated experiments to see it at all? The answer is that the natural state of things in our warm, bright, crowded world is to be measured constantly, and therefore to be definite constantly. Interference is not the rare exception that needs explaining. Interference is what you get in the extraordinary special case where you have worked heroically to shield a tiny object from every stray interaction, cooled it, isolated it in a vacuum, kept every photon and molecule away from it. Only then, in that engineered silence, does the underlying wave nature get a chance to show itself before the world collapses it. The definite, classical world is not a different kind of physics. It is quantum physics with the volume of environmental measurement turned all the way up, which, outside of a few exquisite laboratories, is where it always is. You live in a world that is being measured into solidity around you at every instant, and that relentless measuring is exactly why you have never once had to worry about walking through a wall or finding your keys in 2 drawers at the same time. And yet, having said all of that, having drawn the line firmly, I have to be honest about what is on the other side of it, because the story does not end with decoherence tidying everything away. Decoherence explains, with beautiful precision, why we never see interference in big warm objects, why the classical world looks classical, why the cat is never found in a blur. But it does not, on its own, explain why we see one outcome rather than another. It converts the superposition of paths into something that behaves like a set of separate, non-interfering possibilities. It explains why they no longer overlap and interfere. It does not explain why, out of that set, only one becomes your actual experience, while the others do not. The single dot, the one specific place the electron landed, the aliveness rather than the deadness of the actual cat, that final selection of one from many is still not accounted for. Decoherence tells you why the choices stop talking to each other. It does not tell you who or what does the choosing, or whether any choosing happens at all. The measurement problem, pushed hard, survives even decoherence. And that is why, 100 years on, physics does not have one agreed picture of what is real. It has several, each brilliant, each consistent with every experiment, each demanding that you give up something you did not want to give up. It is time to walk through them honestly and see what the world would have to be like for each to be true. Part 9. The many answers to one question. The oldest of the answers is the one associated with Niels Bohr and Werner Heisenberg, worked out in the city that gave it its name, and usually called the Copenhagen interpretation. Its stance is austere, almost stern. The wave function, on this view, is not a physical thing spread out in space. It is a compact summary of what we can predict about the results of measurements, nothing more. And it is simply not meaningful, Bohr insisted, to ask what the electron was doing between the slits and the screen, because that question refers to something no experiment can ever answer. Physics is about the outcomes of measurements, the marks on the screen, the clicks in the detector, and about those it speaks with perfect precision. The rest, the story of the particle's secret journey, is not a fact the theory is hiding from us. It is a question with no content. When you measure, you get an outcome, and the probabilities are all the theory promises to deliver. If that feels like a refusal to answer the deepest question, that is because it is one, and Bohr thought the refusal was the mature and honest response to what the experiments were telling us. Hugh Everett, a graduate student, found that refusal unbearable, and in 1957 he proposed the opposite extreme. What if there is no collapse at all? What if the wave function is completely real, and it never turns into a single outcome, but simply keeps spreading and branching forever, exactly as the equation says? On this view, when you measure the electron, you do not force it to pick one slit. Instead, you become entangled with it. The version of the world in which it went left and the version in which it went right both continue to exist, fully real, but they no longer communicate, and you split along with them. There is now a copy of you who saw it go left and a copy who saw it go right, each equally real, each convinced that a single definite thing happened, each living in a branch of a universe that has quietly divided. This is the many worlds interpretation. It keeps the mathematics pure and untouched, removing the ugly, unexplained collapse entirely, at the price of an almost unimaginable extravagance, a reality that is constantly branching into countless parallel versions, one for every possible outcome of every quantum event, all of them real forever. Louis de Broglie and later David Bohm took a third road, one that restores the thing Copenhagen renounced and many worlds multiplied. What if the electron is always a real particle, always in exactly one definite place, following one definite path, just as your intuition demanded all along? To make that work, they proposed that alongside the particle, there is a real wave, the pilot wave, that fills space, passes through both slits, and guides the particle's motion. The particle goes through one slit, but its guiding wave goes through both, and the wave's interference steers the particle so that, across many runs, the pattern comes out right. This pilot wave theory is fully deterministic. There is no fundamental randomness, no collapse, no observer required, and the particle has a definite trajectory at every instant. It sounds like a return to sanity, and in some ways it is, but it exacts its own strange price. The guiding wave has to be instantaneously sensitive to the entire experimental arrangement, everywhere at once, which makes the theory explicitly and irreducibly non-local, with influences that span space faster than light in their coordination, even though you can never use them to send a signal. Then there are the theories that say collapse is real and physical, a genuine event in the world, and try to write it into the laws directly. In the model developed by Gherardi, Rimini, and Weber, every particle has a tiny, random chance per moment of spontaneously localizing, of collapsing its own wave function to a point, all by itself, with no observer at all. For a single particle, this almost never happens, so small systems drift in superposition for ages, just as we see. But a large object contains so many particles, so tightly bound together, that the chance of at least one of them collapsing at any instant and dragging all the others with it becomes overwhelming. A cat collapses itself billions of times a second. Roger Penrose proposed a related idea in which gravity itself triggers the collapse once a superposition grows massive enough to warp space-time in incompatible ways. What all these objective collapse models share is that they make collapse a real physical process, potentially measurable, needing no mind and no observer, and they can in principle be tested because they predict tiny deviations from standard quantum mechanics that ever more sensitive experiments are now hunting for. And finally, there are the views that locate the answer not in the particle and not in extra worlds, but in the relationship between the system and whoever or whatever comes to know it. In cubism, the wave function represents an observer's own information, their reasoned expectations about what they will experience, and collapse is just the ordinary updating of that information when a new fact comes in, the way your expectations snap into place when you finally see the result. In relational quantum mechanics, championed by Carlo Rovelli, there are no absolute facts at all, only facts relative to particular systems. An outcome is real for the thing it interacts with, but there is no view from nowhere in which the universe holds a single master set of facts about itself. On these readings, the sense in which reality does not exist until it is looked at comes closest to being literally true, not because a mind makes matter, but because to be a definite fact, on this picture, just is to be a fact for some system, established in an interaction and not otherwise. I want to make sure you feel how differently these pictures answer the single question of our double slit, because that is where their disagreement becomes vivid rather than abstract. Ask each of them the plain question, what did the electron do between the gun and the screen? And listen to how wildly the answers diverge, even though every one of them predicts the identical pattern. Copenhagen says the question has no answer, and you should stop asking it. Many Worlds says the electron did both, and so did you, and there are now two of you, each seeing one result. Pilot Wave says the electron went through exactly one slit as a real particle, while its guiding wave went through both and steered it. Objective Collapse says the electron was a spread that a real physical process snapped to a point somewhere along the way, all by itself. Cubism says the wave function was never the electron at all, but your own information about it, and the question is like asking what a probability was doing before you learned the outcome. Relational quantum mechanics says there simply is no absolute answer, only answers relative to whatever the electron interacted with. 6 answers. 1 experiment, 1 flawless pattern, and no measurement anyone has yet devised can tell you which answer is true, because they were all built, deliberately, to agree on everything you can measure. That last point is the one that makes this so maddening and so unlike the rest of science. Normally, when scientists disagree, they design an experiment to settle it, and the losing idea is discarded. Here, the disagreement was constructed to be experimentally invisible. Every interpretation reproduces standard quantum mechanics exactly, which means every interpretation reproduces every experiment exactly, which means no experiment can currently choose between them. They are not competing predictions. They are competing stories about what the single agreed prediction means. Some physicists find this so frustrating that they refuse to discuss interpretations at all, insisting that if the mathematics gives the right answers, the question of what it means is not physics but idle talk. Others, including some of the deepest thinkers in the field, insist that a theory which cannot tell you what is real is unfinished no matter how well it predicts, and that the discomfort is a signal we are missing something profound. Both camps have been arguing, in good faith, for the better part of a century, over an experiment simple enough to draw on a napkin. Now stand back and feel the size of what you are looking at, because this is the emotional center of the whole subject, and it is not the strangeness of any one theory. It is that all of them are on the table at once. Copenhagen, many worlds, pilot waves, objective collapse, cubism, relational quantum mechanics. These are not the confused guesses of people who lack data. They are the considered positions of some of the most careful minds our species has produced, and every one of them fits the experimental results perfectly, to the last decimal place, with no way yet to tell them apart by any measurement. That is the honest, almost unbearable state of the deepest theory we have. Brilliant, sober people, staring at the exact same flawless results, genuinely cannot agree whether there is one world or countless worlds, whether the particle has a path or does not, whether collapse is a real event or an illusion, whether there are facts about the world when no one is measuring it. This is not a failure of intelligence or of effort. It is the residue that 100 years of the finest thinking has left behind, the irreducible core of not knowing at the foundation of everything we can predict so well. And into that core, the title's claim reaches. Because among these serious answers, a real family of them says that yes, in a precise and defensible sense, the definite reality of the world is not simply there independent of measurement. Let me make the strongest honest case that this family might be right. Part 10. Why it might be right. The reason the title's claim deserves to be taken seriously, rather than dismissed as wordplay, comes from a result that did not exist in the early days of the argument, a result that turned philosophy into something you can test on a bench. For a long time, the sensible hope was that the whole mystery was just ignorance. Perhaps the electron really did have a definite path all along, and a definite everything else, and the wave function was only our incomplete knowledge of hidden details we had not yet measured. Einstein himself favoured something like this. He could not accept that the world had no definite facts until measured, and he suspected that quantum mechanics was correct but incomplete, that underneath it lay a normal world of things with definite properties, a world that was simply there whether or not anyone looked. This is the position called local realism, and it is exactly the comfortable picture your intuition has been fighting to preserve all night. Realism meaning things have definite properties before measurement. Local meaning nothing influences anything else faster than light. It is the common sense view of the world, and almost everyone assumed physics would eventually vindicate it. In 1964, a physicist named John Bell found a way to put that assumption to the test. He considered pairs of particles prepared together and then separated, entangled so that measuring one tells you something about the other, and he proved something remarkable. He showed that if the world really were locally real, if the particles carried definite properties with them all along, and nothing travelled faster than light, then the statistics of certain measurements on the pairs would have to obey a strict limit, a ceiling that Bell wrote down as a precise inequality. And he showed that quantum mechanics predicts those statistics will break that limit, will exceed the ceiling that any locally real world is forced to respect. This was no longer philosophy. It was a number, measurable, that would come out one way if the comfortable common-sense world were true, and another way if quantum mechanics were true. The experiments were done, refined over decades by Alain Aspect, and later by teams around John Clauser and Anton Zeilinger, closing loophole after loophole until, in recent years, the result was airtight, and it earned those three the Nobel Prize. Every time, the quantum prediction won. The limit is broken exactly as quantum mechanics says, and exactly as no locally real world could allow. The conclusion is inescapable, and it is one of the most important things science has ever established. The world is not locally real. You cannot have both. Either things do not have definite properties until they are measured, or there are influences that reach across space in ways that defy the tidy separation of here from there, or both. The comfortable picture Einstein hoped for, the world of definite things sitting there, fully formed, whether or not anyone looks, is ruled out by experiment. Not doubted, ruled out. Nature has told us, in the clearest way we know how to ask, that reality is not simply a collection of pre-existing facts waiting passively to be discovered. It took decades to make the experiments truly airtight, and the story of how is a small monument to scientific care that is worth knowing. Each early test left a loophole, a way the comfortable local realist world might still sneak through. Perhaps the two particles were somehow influencing each other through an unnoticed signal, so experimenters separated them far enough and switched their measurement settings fast enough that no signal, even at the speed of light, could pass between them in time. That is the locality loophole, and it was closed. Perhaps the detectors were only catching a biased sample of particles, so experimenters improved their efficiency until that escape was sealed. That is the detection loophole, and it was closed. Perhaps the choice of what to measure was subtly correlated with the particles in advance, so experimenters used everything from random number generators to the light of distant quasars, billions of years old, to make the choices, ensuring nothing in the recent past could have arranged the correlation. One by one, over 50 years, every loophole was shut. And in 2022, the Nobel Prize in Physics went to Alain Aspect, John Clauser, and Anton Zeilinger for exactly this work, for turning Einstein's philosophical hope into a settled experimental fact and showing, beyond reasonable doubt, that the world does not obey local realism. Let that sink in as a plain statement, stripped of all the interpretation. The most careful experiments humanity has ever performed have shown that the universe cannot be both local and real, in the everyday sense. It cannot be a collection of separate things, each carrying its own definite properties, minding its own business, uninfluenced by distant events, sitting there, fully formed, whether or not anyone measures it. That picture, the picture every one of us walks around with, the picture that feels like simple sanity, has been tested against nature as directly as anything ever has, and nature has rejected it. Something about that comfortable image is false. Either the definiteness is not there before measurement, or the separateness is not real, and the world is threaded through with connections that ignore distance, or both. This is not speculation, and it is not one school's opinion. It is the experimental verdict, agreed by everyone, whatever interpretation they favour. The common-sense world is gone. What we argue about now is only which strange replacement to accept in its place. This is why the title's claim is not fantasy. Once local realism is dead, the idea that the definite properties of the world come into being in the act of measurement, rather than sitting there beforehand, stops being mysticism and becomes one of the reasonable options left standing. Wheeler, who gave us the delayed choice, drew exactly this conclusion and pushed it as far as it will go. He spoke of a participatory universe, a cosmos in which observation, in the physical sense of measurement and the making of records, is not a passive reading of a finished reality, but part of the very process by which reality acquires its definite character. He liked to say that no phenomenon is a real phenomenon until it is an observed or recorded phenomenon. The past, on his view, is not fully fixed and then read. It is, in part, brought into definiteness by the measurements that reach back and close the question, exactly as the delayed choice experiment seemed to show. The universe, in this picture, is not a finished thing we look at. It is something that comes into focus, fact by fact, through the countless measurements that its own parts perform on one another. I want to be scrupulous about what this does and does not license, because the line matters more here than anywhere. It does not license the idea that your mind creates the world, that thinking makes things so, that the universe bends to your wishes. Measurement in this sense is done by any interaction that makes a record, and the universe has been measuring itself with rocks and light since long before there were minds. What Bell and Wheeler license is something colder and more precise. They license the claim that definiteness itself, the property of the world being one specific way, rather than a spread of possible ways, is not a freestanding feature that exists independent of measurement. They license the claim that the act of measurement, the making of a record through interaction, is woven into how facts come to be facts, rather than being a bystander that merely notices facts already complete. That is a real and defensible reading of the strongest experiments we have. It might be right. A great many careful physicists think something like it is right. And if it is, then the plainest experiment in physics has been telling us all along, in the quiet language of stripes appearing and vanishing on a screen, that the world we thought was simply out there, finished and independent, is instead something more like a conversation, a reality that settles its facts in the very act of being examined. But I owe you the other side, because honesty requires it, and because it is where the humility lives. It also might not be right. Many worlds says the definiteness is an illusion of your particular branch, and nothing is ever created by looking. Pilot wave theory says the particle had a definite path the whole time, and local realism died only because the world is non-local, not because facts wait on measurement. Objective collapse says definite facts are made by a physical process that needs no observer at all. Each of these keeps every experiment intact and denies that observation makes reality. So the truthful statement is not that reality certainly does not exist until you look. The truthful statement is that this is one of a small number of serious, surviving possibilities, that the common-sense alternative is dead, and that we cannot yet tell which of the strange survivors is the true one. That is where a century of the finest work has left us, and there is a kind of peace in saying it plainly. We do not know. And now, having stood at the edge of that not knowing, let us come back down, all the way back to the ordinary room you are lying in, and ask what any of this means for the solid, reliable world you are about to fall asleep inside. Part 11. The solid world you never stopped trusting. You might reasonably worry after all this that the ground under you has been quietly pulled away, that if the world does not carry definite facts until it is measured, then nothing is reliable, and the solid room around you is some kind of trick. Let me set that worry down for you, because the truth is almost the opposite, and it is genuinely reassuring. The reason your world is solid and dependable is the very process we met earlier, decoherence, working ceaselessly and everywhere, and it is precisely what keeps the strange open-endedness of the small scale from ever leaking up into the room you live in. The quantum haziness is real, but it is also fantastically fragile, and the ordinary world is far too warm and busy and interconnected for it to survive there even for an instant. Consider what it would take for you to ever see a chair in a superposition of two places. Every atom of the chair would have to stay perfectly isolated from everything else, untouched by any air molecule, any photon of light, any breath of heat, because the slightest such contact records the chair's position and destroys the superposition. But a chair sits in a flood of light, bathed in air, radiating warmth, touched by its surroundings trillions of times every second. Each of those touches is a measurement in the physical sense, a record made through interaction. The chair is being measured relentlessly by the whole world around it, far faster than any quantum spread could ever build up. So a chair is never in two places, not because chairs obey different laws than electrons, but because chairs can never escape the constant measuring gaze of their environment for long enough to become uncertain. The same rule that lets a lonely electron spread through both slits is exactly the rule that nails a chair firmly into one place, because the chair, unlike the sheltered electron, is never alone. This is the quiet resolution of the whole tension. The wave of possibility never goes away. It is still there, underneath everything, the true description of every particle in your body and your bed and the walls of your room. But in anything large and warm and connected, that wave of possibility, not a wave of stuff, spreads across so many interacting pieces and gets recorded by the environment so instantly and so thoroughly that its open possibilities are pinned down into ordinary facts, faster than you could ever notice. The strangeness has not been removed from the large world. It has been diluted into it so completely, spread so thin across so many constant measurements, that what remains is exactly the steady, definite, trustworthy world of your experience. Solidity is not the absence of the quantum haze. It is the quantum haze, measured into stillness by everything around it, moment after moment, without pause. And far from being a fragile curiosity, this small-scale strangeness is the foundation the modern world is literally built on. Every transistor in the device playing this to you works because electrons are waves that can slip through barriers they classically should not be able to cross, a purely quantum behavior with no classical explanation. The entire electronics industry, every computer, every phone, rests on engineers taking the wave nature of matter seriously and putting it to work. The chemistry of your own body, the way atoms bond into molecules, the shapes of the proteins that keep you alive, all of it is set by the wave nature of electrons, arranging themselves around atoms, according to the same mathematics that paints the stripes on the screen. The colors of things, the stability of matter itself, the reason atoms do not simply collapse, every bit of it comes from the quantum rules we have been circling all night. Even the sun shines because of a quantum effect, particles behaving as waves to tunnel through a barrier and fuse when the ordinary laws of motion say they should not be able to. You are alive right now, warmed by starlight that only exists because reality at its smallest scale does not obey the rules your intuition insists on. There is a gentle irony worth savouring in all of this. the strangeness we spent the night worrying over, the spread of possibility, the refusal of things to be definite, is not some flaw in reality that we must overcome. It is the source of everything stable we depend on. A world made of hard little classical particles, obeying only the old rules, would be a dead world. Atoms could not hold together, stars could not shine, chemistry could not build a living thing. It is precisely because matter is a wave of possibility, not a wave of stuff, that anything solid and lasting can exist at all. The very feature that unsettles us is the feature that makes us. So the very same physics that refuses to tell you whether the world is definite when unmeasured is also the physics that makes the world work, that lights your screen and bonds your cells and fuels the star that made every atom heavier than hydrogen in your body. This is not some fringe effect at the edge of knowledge that you can safely file away as irrelevant to daily life. It is the operating system underneath daily life. The mystery is not off in some laboratory. It is in your hand, in your chest, in the light coming through your window. You have been living inside the answer to the deepest unsolved question in physics your whole life. Using it, depending on it, made of it, and never once needing to resolve the question to do so. There is something calming in that, I think. The universe does not require us to understand it in order to hold us up. It was doing all of this, measuring itself into solidity, tunneling light out of stars, arranging atoms into living things for billions of years before anyone framed the question. And it will go on doing it whether or not we ever settle what it means. Let me linger on the tunneling for a moment, because it is the quiet hero of your daily life and almost nobody knows its name. Tunneling is the pure double-slit strangeness in another costume. A particle, being a spread of possibility rather than a point, has some of its wave function reaching into places a solid particle could never go, including through the far side of a barrier that, by the old rules of energy and motion, it should not have enough force to cross. Most of the time it does not cross. But sometimes, because the possibility was there, it simply appears on the other side, having passed through a wall it could not climb. This sounds like a party trick, and it is the reason the sun shines. Deep in the sun's core, the particles that need to fuse together are repelled by their like charges, and by the ordinary laws, they almost never have enough energy to touch. If those old laws were the whole story, the sun would not burn, and you would not be here. But because those particles are waves of possibility, a tiny fraction of them tunnel through the barrier of repulsion and fuse anyway, and that tiny fraction, multiplied across the unimaginable number of particles in a star, is enough to light a sun for billions of years. The warmth on your skin from sunlight is the direct product of the same wave nature that let a single electron go through both slits. Without it, the sky would be dark and cold and empty of us. And the same effect runs the machines of the modern world. The flash memory that stores your photos works by deliberately tunneling electrons through a barrier that would be impassable to a classical particle, trapping them there to hold a bit of information. Certain kinds of microscope, sensitive enough to image individual atoms, work by measuring the tiny tunneling of electrons across the gap between a needle and a surface. The transistors that make up every processor depend on controlling where the wave nature of electrons lets them flow and where it does not. And as those transistors have shrunk to only a handful of atoms across, engineers now fight against unwanted tunneling. Electrons slipping through barriers meant to stop them, as one of the central obstacles to making chips smaller. So the wave of possibility, not a wave of stuff, is not some abstraction locked away in a philosophy seminar. It is the working principle of the device in your hands, the light of the star that made you, and the chemistry of the body reading these words. You are, in the most literal sense, a structure built and powered by the very strangeness we have spent the night trying to understand. Which brings us gently back to where we started, to that plain little experiment, a source, 2 slits, a screen, and to the strange soft fact it has been trying to tell us all along. We have followed it as far as it goes tonight, from the ripples on a pond to the death of local realism, from a single electron's impossible journey to the honest confession that the finest minds in physics cannot say what any of it finally means. And now, before you drift off, I want to gather it back up into something small enough to carry with you into sleep. Something about what it means, for you, to open your eyes each morning and look at the world. Because the experiment, in the end, is not really about electrons. It is about looking, and what looking is, and whether the simple act of it is as innocent as it has always seemed. Part 12. What it means to look. Think about what you did without a second thought, the last time you opened your eyes in a dark room. You looked, and the world was simply there. The shapes of the furniture, the light at the edge of the curtain, all of it waiting for you, finished, as though it had been sitting there fully formed, whether or not you woke. That is what looking has always felt like. A passive act. The world is out there, complete, and looking is just letting it in. A window opening onto a scene that was already there. Everything about the way we live assumes this. The world is the stage, and we are the audience, and the play goes on identically whether or not anyone is watching. The plainest experiment in physics has spent 100 years quietly suggesting that this picture is not quite true, not wildly false, not in the way that would let your mind reshape the furniture by wanting to, but not quite true, in a way that is subtler and stranger and harder to shake off once you have seen it. Because at the smallest scale, where everything you are made of actually lives, the world does not seem to carry a full set of definite facts about itself at all times, sitting there independent of any measurement. It seems to hold possibilities open, genuinely open, until an interaction, a measurement, a record made, closes them into one fact. And every time anything looks, in that physical sense of interacting and recording, a little more of the world's open possibility is settled into the way things definitely are. The universe keeps no record, and reality stays a wave of what might be. A record is made, and reality becomes a fact. And you, every time you open your eyes, are one of the countless places in the universe where records are made, where the haze is measured into stillness, where the possible becomes the actual. That does not make you the center of anything. The universe was doing this with rocks and starlight for billions of years before you, and it does not need you. But it does mean that the ancient, comfortable line between the watcher and the watched is not as clean as it feels. You are not standing outside a finished world, looking in through a window. You are inside the process, part of the vast ongoing measurement that the universe is always performing on itself. One more interaction among the endless interactions by which reality settles its facts. To look at anything, even in the smallest and most ordinary way, is to take part, however slightly, in the world becoming definite. The act of looking, which felt like the most passive thing you do, may be one of the ways the world comes to be one specific way, rather than a spread of ways. Reality is not simply what you observe. It is, in some part, we still do not fully understand, something that happens in the observing. And the wave of possibility never truly leaves. It is still there tonight, underneath your still and solid room, in every atom of you, spread too thin across too many quiet measurements to ever show itself. But there. You are, at this very moment, a spread of possibility measured into a single definite person, by every breath of air and beam of light that touches you, held in focus by a universe that will not stop paying attention. There is nothing to fear in that. It is the same gentle process that keeps your room solid, that lights the stars, that has held the world together with perfect reliability since long before the question was ever asked. You can let the question stay open. The world will keep settling itself into place around you, fact by quiet fact, whether or not you ever solve what that settling is. I find something quietly steadying in ending here, rather than on a solved problem, and I want to leave you with why we live surrounded by a pressure to have answers, to resolve every uncertainty, to know. And this experiment, the plainest one in all of physics, refuses to give us that. It tells us with total precision exactly what we will see, and it declines absolutely to tell us what it means. 100 years of the most capable people who have ever lived have stood where you are standing tonight and come away without the final answer. That could be read as a defeat, but I think it is closer to a gift. It means the world still holds a genuine mystery at its foundation, not a mystery of ignorance that better instruments will clear away, but a mystery that sits inside the best knowledge we have, woven into the light and the matter and the act of looking itself. You do not have to solve it to fall asleep beneath it. You only have to let it be what it is, which is astonishing. So let the question stay open, the way the world itself seems to keep its smallest facts open, until they are gently settled by being seen. There is no urgency here, nothing to fix before morning. The universe has been measuring itself into a solid, reliable, trustworthy world for 13 billion years, and it will go on doing so through the night, holding your room in place, holding you in place, one quiet interaction at a time. Whether or not either of us ever understands the trick of it, that is enough. That has always been enough. Thank you for spending this time with me, and for letting your mind wander this far into one of the strangest and most beautiful puzzles we have. If you enjoyed drifting through the double slit tonight, a quiet like or subscribe genuinely helps this small channel grow, and it means more to me than you know. And remember, the next time you open your eyes in the dark and the world is simply there to meet you, that the looking may never have been quite as innocent or as separate from the world as it always seemed. Good night, and may you never look at the simple act of looking the same way again.